Hey guys, so this is actually our last video. We made it. I hope you found all the other videos this week to be somewhat useful. And I'm sure if you're going into chemistry later on, they will be. Now, let me just tell you one thing about Google Classroom. Is that they're shutting Google Classroom down for the summer. They might not reappear in September. So whatever you need or whatever you think is important, download them, store them somewhere. Okay, I would advise you if you were to store my videos, try to get yourself an external hard drive at the same time. All the mistakes I've been making, I mean, you won't be able to locate them on the splash page anymore, so you might have to write them down somewhere. That video on esters has various different mistakes. You get the idea. All right, so this is our last lesson. It's on hydrolysis. Now, hydrolysis is a reaction where water split. Right? That's what the word hydro means, and of course followed by the word lysis. So water splitting. So what's so important about this? I heard about this before. I heard about this for many years. Well, what we're trying to illustrate here is a reaction of that happening. Okay? Because if you have an ion and you're reacting this ion with water, the result of that can be acidic or basic. In another word, salt. Okay, salt. If I were to ask you, what is the pH of salt? A lot of people will say, well, it's not, there's no H's, there's no OH's, it's going to be neutral, man. Well, that's where you're wrong. Some salt are actually acidic. Some salt are actually basic. The reason why a lot of you would say salt will be neutral is because you would tend to think about table salt, sodium chloride. Now, sodium chloride, if you dissolve it in water, oh yeah, that's neutral. That's for sure neutral. Okay, it's salty. It has to be. Okay, it's not acidic because it's not soury. Imagine sour salt. Oh my goodness, it's not bitter. I hope it's not, so it's not really basic. It is salty, like me. Okay, like some of you said about me. All right, so let's write this down. Okay, I have 4 scenarios here. Scenario number 1. Okay, we have salts made up. Okay, well, not really made up. Okay, salt formed. Neutral solutions. Okay, which salt are neutral? Okay. Now, I'm going to have a little thing right here that you guys have heard from. Okay, and that is the list of strong acid and the list of strong base. Now, if you remember back a while ago, okay, I said that these guys are all strong acids. These guys all dissociate completely, and they would result in a very low pH. Okay, so these are all the strong acids. Let me just keep that here for the rest of this lesson. And these are all strong bases. NaOH, KOH, LiOH, BaOH2. Now, are there more? Or that is it? There's actually more strong acid. There's actually more strong base. I'm just not listing them all. But what I want you to know is to illustrate how salts can sometimes have a certain pH other than 7. Right? All right. Knowing that. So, which salt are neutral when dissolved in water? Okay. So let's write this down. That's salts made up of cation of a strong base. Okay, like Na+. That's a cation of a strong base, right? There we are, strong base. And anion of strong acid, such as chlorine. Okay? Chlorine is part of a strong acid anion. So together, if you were to make a salt out of this, that salt will be neutral because sodium is a strong base cation. Chlorine is a strong acid anion. Therefore, both of these are strong. Both of these tends to, I guess, not react with water. As a result, the water stays neutral. Remember, water can act as an acid or a base. Water can split, as in hydrolysis. Okay, will chlorine cause water to split? No. Will Na cause water to split? No. Therefore, water won't split. Water won't split. You won't have an excess of OH. You won't have an excess of H. As a result, that's why sodium chloride remains neutral. Let's write this out. Okay, will have no effect on the pH. Okay, now, biggest reason here is this. This is the biggest reason, which I'm going to put in parentheses, that the stronger the acid, or the stronger the base, the stronger the acid, we will say that the weaker its conjugate base. Now, hopefully you can go back to my lesson back in January, I think. I don't remember. Well, it could have been February or even March. Actually, maybe in the beginning of March. What are conjugate base, conjugate acid, and stuff like that. Hopefully you can go back there and take a look. But I will actually do a little review here in terms of what that is later on when we looked at salts forming other solutions. But yeah, this is a very important sentence right here. Very, very important in the form of hydrolysis. That the stronger the acid, so these guys are all strong acid. But if you were to look at its conjugate base, it's actually a weak conjugate base. So weak that the dissociation is a one-way. So weak that this conjugate base might not go back. Okay? So the stronger the acid is, which is all of these guys, its conjugate base, in this case, Cl-, will have a very, very, very hard time trying to go back to become HCl. Okay? So let me just give you a little example right here. HCl, okay, plus water will give you H3O plus Cl minus. Notice my arrow is one way and not the other way. It's because HCl minus, which is the conjugate base of this reaction, is so weak that it doesn't want to proton accept to become HCl anymore. Okay, that's why this reaction is not an equilibrium. It's because this guy is pretty much impossible to go back to this guy. So this reaction is a one-way reaction. We know this kind of information because HCl is a strong acid. They dissociate completely in solution. Okay, it is when the acid is weak, that's when it can go backward, because in this case, the weaker the acid, the stronger its conjugate base, right? So if your conjugate base is strong, it wants to hydrogen accept. Go backward, man. But not in this case. Okay. All right. I hope you get it. So let's look at salts that are acidic. Oh, acidic salt. Wow. Now, stop thinking about table salt. Okay, because when you're thinking of table salt, you think of saltiness, you think of sodium chloride, but of course there are thousands and thousands of salt. Anything with a cation and an anion and dissociated water, they are all salts. Okay, so we're looking at salts that form acidic solutions. Let's do an example. Okay, example here, of course, is this salt right here called ammonium chloride. Okay, this is an acidic solution salt because it forms an acidic solution when you dissolve it. So if somebody will ask you NH4Cl, okay, ammonium chloride salt, oh, what's the pH of that? And if you say 7 because it's a salt, man, there's a lot of things that you need to know. Okay, now NH4Cl, okay, dissociate in water. So if you put that in water, you're gonna get NH4 plus and Cl minus. All right, that's what happens to all salts when you put in water, especially the ones that are soluble. They will break apart into their component ions. Then you look, okay, all right, is this guy, which we saw before, is this guy going to react with water? Meaning, is he a good conjugate base? The answer we already defined. No, he's not, because Cl is part of a strong acid. It's an anion of a strong acid. So if you're an anion of a strong acid, you are not doing anything. You're not reacting with water. But what about NH4? Is he a cation of a strong base? Well, he's no Na, he's no K, he's no Li, he's no Ba. You are not a metal or a cation of a strong base, which means you have the potential to be a strong conjugate acid. You would love to donate one of these guys. And that's exactly right. And that's exactly true. Because NH4 would love to react with water. Oh yeah, I would love to react with water. And in a solution, there are lots of water. Okay, this guy is not gonna break apart to this and this without the addition of water, right? How you dissolve something without water. So when you put this guy in water, it will dissociate. This guy says, water makes me dissociate. Not only that, I will react with you too. In an equilibrium that has a certain Ka value, where this guy is going to be a proton donor. This guy will be a proton donor because I'm a very good conjugate. I'm a very good acid in this case. Mixed water saying that, okay, if you're going to donate proton, I'm gladly to accept one of your proton because, hey, I become H3O plus. Now, no problem with that. Plus NH3. You see that? Okay, one of the H's came over here because water now is acting as a proton acceptor to become H3O. NH4 says already that I'm going to be a proton donor to become NH3. Okay? NH3, of course, is a conjugate base. It's a weak base. Okay, to be exact. It has a certain Kb value. All right. Hopefully you understood all of that, okay? Because that's, again, it's a very important concept of how certain salts can be acidic. Because when it dissociates, one of the participant, in this case the cation participant, reacts with the water to form H3O. So whenever you're making H3O, you're making the solution acidic because H3O is, the entity of making pH lower. H3O is the same thing as H+. I hope you remember. Okay. Oh wait, this is supposed to be number 2. This is scenario number 2. So we're going to look at scenario number 3. That salts that form basic solution. Okay? Is there going to be a time where form a basic solution? Of course. So as an example here is sodium acetate. Okay? This salt is a basic salt, meaning that it forms a basic solution where the pH is going to be above 7. Why? Because NaCH3COO, when you put that in water, it will break apart to give you Na plus and CH3COO minus. Now, again, you might want to ask yourself, Na, is that a cation of a strong base? Oh, yes it is. Yes it is. So Na is not going to do anything. Okay? Na is not going to do anything. Na is actually a metal of a strong base. What about acetate? Is acetate the non-metal of a strong acid? Well, nope. Acetate is not one of these guys. Acetate is a conjugate base of a weak acid. Therefore, I will react with water. I'm a strong conjugate base of a weak acid. So therefore, you bring water near to me, I will react with it. I'm a strong conjugate base, so therefore I would love to proton accept. Who I'm going to take protons from? Well, hello there, H2O. Let me take one of your protons away. So I can become CH3COOH. I love being that, which makes you an OH minus. Poor you. Okay? As an OH minus, as a chemical that creates OH minus, I made this solution basic. Just like how NH4 made the solution acidic, I made the solution basic. As a result, this salt, when dissolved in water, will create a basic environment, so the pH is going to be above 7. Okay. Hey, we're going to do a couple of calculation examples later, so that will really help you in terms of quantitatively exactly what's the pH at a certain concentration of these salts. Okay, that's going to be fun. Okay, a really great way to end this course. All right, let's erase all of this thing. Oh, that should be, oh yeah, never mind. I'm looking at something else. All right, number 4. Okay, scenario number 4 is when you have what we call a double scenario, that salts that act as acid and bases. Can we have a scenario like that? And the answer, of course we can. This popular salt right here. Okay, ammonium cyanide. Oh, this stuff is poisonous. It's really, really bad. So don't eat it. Don't put that in your French fries. Ammonium cyanide. When you put that in water, you're going to get ammonium, okay, cation, and you're going to get cyanide anion. Okay? Oh, somebody wants to be my friend in Fortnite. All right. So, NH4. Take a look at the cation. Take a look at the base, strong base. Is he one of the metal of the? Is he one of the cation of a strong base? No, you're not. So therefore, you are a very strong conjugate base. Okay, you would love to donate one of your H's. Well, what about CN? Is CN a non-metal of a strong acid? Oh, you're not neither. So we have a scenario where this is a potential good conjugate acid. This is a good potential conjugate base. So both of these, okay, both of these will react with water. One will do this, making the solution acidic. Oh, what am I doing? Oh, I messed up the color. No big deal. Every time I make a mistake, I'm making this video bigger in terms of memory. So I have to stop making these things. All right. HCN plus OH. Okay. CN is going to do that. And NH4 at the same time will do this. Okay, so in reality here, ammonium cyanide can be acidic and can be basic, in this case simultaneously. But if you were to dip a pH meter into a solution of ammonium cyanide, it's not going to give you two values. Oh, I'm going to give you an acidic value, and then I'm going to give you a basic value. No. It's going to give you one value. It's going to give you a pH value. But the question is this: is it going to be an acidic solution or is it going to be a basic solution? Well, that all depends in this case on the dissociation constant of NH4, okay, and CN minus. What do I mean by dissociation? What do I mean by, not dissociation constant, sorry, equilibrium constant. So we need to find out what the Ka of this is, okay? As a proton donor, I looked at the CRC handbook that the Ka for this guy is 5.8 times 10 to the power of negative 10, okay? That is his equilibrium constant. And by looking at the CRC handbook, I made the calculation that Kb, because my CRC handbook only gives me Ka, so I have to make the conversion to Kb, is 1.6 times 10 to the power of negative 5. Now, remember, what these number means is their ability to dissociate, okay? The bigger the number, the more likely the dissociation will occur, or the more dissociation it will occur. Dissociation is going to occur, but the bigger these numbers are, the more product of this you're going to get. So if you're going to compare this dissociation, if you're going to compare this versus this, okay, in terms of, is this guy going to be more willing to proton donate versus this guy more willing to proton accept? Because for these values, they're based on the concentration of the product, right? These guys will be in the numerator. So these guys are big, which makes this number big. Now you're comparing two numbers, okay? The equilibrium expression for this and the equilibrium expression for this, stating, of course, am I going to get more product here than here? Well, let's take a look at these values. This is to the power of negative 10. That's small. This is small too, to the power of negative 5, but not as small as this. So by looking at the number, this is a bigger number. Kb is greater than Ka in this case, meaning that in this solution right here, you're getting more of these product than these product, meaning that you're going to get more OH than you're going to get H3O. So therefore, this solution will be basic. Because the dissociation constant says these products, okay, are going to be more than these products based on the comparison of their K value. All right, so if somebody asks you, ammonium cyanide, is it acidic or basic? First of all, you need to know it's not neutral, okay? Because this guy is not a cation of a strong base. This is not an anion of a strong acid. So no, they're not going to be neutral, okay? Second of all, by looking at this guy's Ka and this guy's Kb, which one is bigger? Okay, the bigger wins. If the Kb is bigger than the Ka, like this one, solution will be basic. If it's the other way around, it will be acidic. Okay, very theoretical. So knowing that, okay, after going through all this theoretical stuff, let's look at some application stuff. I have a couple of questions for you. One I do, one you do, but I will give you the answer because I won't see you anymore. Why did I write wrong? Example 1. Okay, I want you to calculate the pH of 0.1 molar of sodium nitrate. Sodium nitrite. Sodium nitrate. If it's sodium nitrate, it would be 7. Okay, because sodium is a metal of a strong base, and nitrate is NO3, and that is actually an anion of a strong acid. That would be 7. But hey, sodium nitrite. This guy ain't no anion of a strong acid, so most likely you are a beautiful conjugate acid. Right? So, NaNO2, put that in water, you're going to get Na plus and NO2 minus. This guy, okay, is a conjugate base of HNO2. Okay, HNO2 is a weak acid. Okay, this makes you a strong conjugate base. Okay, all right. But that's not what I want to know. I don't want to know if this is going to be, a base. I want to know how base. So what I want to do, I want to calculate the pH. So if you know for a fact that NO2 minus is going to be a conjugate base, it's going to be a base, okay? It's a conjugate base of a weak acid, but it's really acting as a base here because I'm going to be reacting with water. Okay, what I want to do? Well, as a base, I want to take your protons. Make the solution OH minus. Right? All right, ice table time. So this guy started out as 0.1. Okay, now I really should show you why 0.1 before I give you 0.1. It's because this is 1 to 1. So if this is 0.1, this is going to be 0.1. Okay, because the ratio here is 1 to 1. If you do your stoichiometry, you really don't need to do a thing because you'll be multiplying by 1 over 1. Okay, so that's why initially NO2 will be 0.1 molar. We don't do anything with water, remember? So in the solution, we start out with nothing, okay? No common ion effect. This will be negative X. These will be positive X because these guys are going to get bigger. Minus X. These will be X. All right? Now, if you were to go to the CRC handbook, you'll notice, of course, that Ka is 7.2 times 10 to the power of negative 4 for nitrous acid or hydrogen nitrite. Okay, so you need to find that information. You're not going to find Kb for nitrite. Okay, you're never going to find that. Maybe for a CFC handbook that is very, very complete, you might find the Kb of this. But you're not going to find the Kb of this. Okay, you're just going to find the weak acid of this conjugate base. Okay, and the weak acid for this conjugate base is HNO2, and the Ka value can be easily detected to be 7.2 times 10 to the power of negative 4. What that means is that you can't use this number for the equilibrium expression because you're looking for OH. You need to find Kb from this. And you know how to find Kb, right? That's just Kw over Ka. Kw is a constant, 1 times 10 to the power of negative 14 over 7.2 times 10 to the power of negative 4. Okay, that will give you 1.4 times 10 to the power of negative 11. Oh, I hope I'm right. I hope I'm right. Okay, so that's the Kb value. We need that because Kb expression is based on, of course, HNO2 times OH minus, which we want to find, over NO2. Okay, so if you would have plugged that in, you would have done x times x over 0.1 minus x. Good thing, of course, is that I can easily tell that 100 rule will be useful. So this is going to be gone. So what you have, of course, is x equal to 1.2 times 10 to the power of negative 6. Okay, I have my calculator handy here. So that's x. So to calculate pH of the salt, pH is equal to 14 minus negative log of this number. Okay, just as we expected. The answer is about 7. So that's how you calculate the pH of a salt that ain't neutral. Okay, so let's review this a little bit. First, you're given a salt, right? You know this is not neutral because one of the participants is a conjugate base of a weak acid. So this guy likes to take H's from H2O, which he did, and create a basic environment. Put it into your ice table to calculate what at equilibrium, what would this value be? And we did that right here. Thank goodness we avoid x is such a small number that we don't have to go through the quadratic equation. pH will be 14 minus the negative log of this number to give you this. Okay, I guess one of the things that a lot of students make mistakes of course, is that some students would actually use Ka here. Okay, you have to be very careful. Okay, you have to be very, very careful. First of all, you're not going to find Kb for this. This is I don't think I've ever seen a list of Kbs because there's so many. But then there are, of course, lists of Kas for the acid, the weak acid counterpart of this conjugate base. So you're going to have to look for these guys. Okay? And you need to be able to see the fact that I can't use this number. I need to find the Kb of this number by dividing it with Kw. Some of the tricks that you may encounter later on, if you're thinking of going into the chemistry realm, this is actually very important because for a lot of IB exam, for HL IB exam, which you guys are not going to be, writing or seeing, okay, they have questions of calculating pH of a salt. Let's see if anybody is unprepared enough to think that there's 7 every year. All right. Hey, let me give you one to do. Okay, and we're going to conclude this course right now. Okay, I think you guys heard enough of me. Example 2, 0.2 molar of, I don't know, NH4Cl, okay? Ammonium chloride. We've gone through, I don't think we've gone through this. First of all, you need to find out that, oh, is this going to be 7? I can tell you it's not going to be. Why would I do that, right? Then you have to find out, is this going to be an acidic salt or a basic salt based on what it dissociates into? All right? Then you calculate, okay? Then you calculate. But since I'm going to give you this number, you pretty much know for a fact that what you're trying to find, because I'm going to spare you from looking into CRC by giving you the Ka of NH4 plus. What a big clue. Okay. Anyway, the answer I worked out is going to be around 4. Okay, so it's an acidic salt. See if you guys can get the same thing. Hopefully I didn't make any mistake in terms of finding the CRC number for you. At least I didn't have to convert it for you. Hopefully I didn't make a mistake by doing the ice table and everything to get the answer of 4. But you let me know. Okay. Actually, I'm not sure if you'll let me know, because remember, by the end of tonight, I hope you guys have downloaded everything that you wanted. Write down everything that is important. Because they're shutting down Google Classroom. I think they're resetting it. That's what I've been hearing. I'm not sure if it's true, but better be safe than sorry. Get yourself a portable drive. Download all my videos. I'm so sorry, but I'm not sure why I record these video under 1080p, because really that does not need to be. So one of these video, sometimes 45-minute video will cost you around like 700 megs. 700 megs, that's a lot of memory. Okay, so get yourself a portable hard drive. If you think it's necessary, that you think you're going to go into chemistry later on, download those videos in there, or just download it for the sake of reference. And guess what? That's it. You don't have to hear from me anymore. Okay. This course is complete, and I gave you more in terms of what the regular grade 12 would have learned also, and what the HL people would have learned also. So yeah, you can even share this with your HL friends. Okay, who's going to be taking HL Chem with me in September. Yeah, they're going to be taking HL Chem with me in February, actually, next February. So your HL friends who are doing SL Physics right now will have me as their as I will finish off this course with them. You can let them know. They don't know that yet. Anyhow, I want you guys a great summer. Okay, just chill. And hopefully, cross my finger, I'll see you in September. All right. Have a good summer, guys. Let's wrap it up. Bye.